Hi, everybody. My name is Dylan. I'm happy to be here to help celebrate 30 years of PMIP with everybody, and happy to share some new results that we've got, summarizing some model simulations targeted at looking at North American hydroclimate response to different ice sheet characteristics and how ocean coupling might influence the large-scale response to those different ice sheet characteristics. So quick shout out to my co-authors on this, Alan Seltzer at Hui, Chris Karnauskas at CU Boulder, Juan Laura at Yale, Sally Zong at Johns Hopkins, and Pedro Denizio also at CU Boulder. So yeah, I think Bart, Brian, and Clay did an amazing job of setting the stage for me here. I don't think I need to remind everybody, particularly this group, what the proxy reconstructions show. You could tell me way better than I could ever summarize it for you. But I think we all know that during the LGM, the Southwest US was much drier than it is today, and the Pacific Northwest was much, I'm sorry, reverse. The American Southwest was much wetter than it is today, and the Pacific Northwest was much drier than it is today. And proxy reconstructions show that pretty definitively. Model simulations show that pretty definitively. And the question for as long as we've had these reconstructions is why? What are the physical mechanisms that connect the different boundary conditions that we saw during the LGM to the drastically different hydroclimate response that we saw along the North American West Coast? And for one of the longest standing hypotheses for why this might be was this idea, as Bart has alluded to, of a rock in a stream, where you have this massive ice sheet sitting over North America. It's 3 kilometers tall in some places, and it physically, mechanically diverts the jet stream either southward or splits it. Parts of it goes north, parts of it goes south. But all told, the storm tracks are shifted in such a way that the majority of that rainfall gets to the Southwest United States, and less of it is getting it to the Pacific Northwest and giving you that shift in the hydroclimate. But what we'd like to do today is just sort of revisit this question using a variety of new tools, and also sort of building on previous work, thinking about this question by separating it into different ice sheet characteristics, but also taking into account the range of effects that different kinds of ocean coupling can have. So these are our research questions for this particular topic. Can we separate the mechanical versus thermodynamic influence of continental ice sheets on West Coast hydroclimate? More specifically, we're looking at the influence of these different ice sheet characteristics on the North Pacific jet stream and downstream rainfall over the western part of North America. And then also, can we isolate, what is the role of air-sea interactions and or ocean dynamics in modulating the response of the climate system to these different ice sheet characteristics? To address these questions, we're going to use a suite of CSM1, so Community Earth System Model, CSM 1.2 simulations that were conducted by Pedro Denizio et al. In 2018. We just got the output and we were lucky enough to be able to analyze it. So we really appreciate their efforts. I'm going to show you results today from 3 of these simulations. There was a full LGM simulation, which has all of the boundary conditions that you would expect to be shifted relative to PMIP3 protocols. We'll also look at what we call a white mountain simulation, which is just isolating the impact of topographical forcing from the ice sheet, in addition to its brightness, so its albedo, thermodynamic forcing. So we're just forcing the model with those 2 boundary conditions set to LGM levels. Everything else is pre-industrial. And then a third simulation that we call a green mountain simulation, which is just the topographical forcing and the surface characteristics of the ice sheet. Even though it's really tall, the surface characteristics are going to be set to pre-industrial levels, so that ice sheet is tall and relatively dark, so it's not as shiny, less thermodynamic forcing. In addition to these different single forcing experiments, Pedro Denizio and friends ran a suite of ocean configurations with their white mountain, green mountain, and control simulations. There's a pre-industrial control simulation as well. And this, the differences between these different ocean configurations will let us know the importance of air-sea interactions versus dynamical ocean forcing. So we have an AGCM only setup where we have just the atmospheric model responding to the changes in boundary conditions. The climatological SSTs are fixed to the control values. There's a slab ocean model configuration, or SOM configuration, where we have a very thin ocean. It's about 50 meters deep everywhere. It allows for air-sea heat exchange, but there's no ocean circulation there's no dynamics in the ocean to move heat around. And then finally, there's the dynamical ocean model, which is the full gauntlet. It has AMOC, it has currents, it has gyres, all the things. And that will be, our full setup as well. So let's get into the results and see what we see in these different experiments. We'll start with the full LGM setup to get a sense for how this model is responding to the full gauntlet of boundary conditions, and then we'll start to peel back some layers. So these are the wintertime atmospheric circulation anomalies in our full LGM simulation. This is the zonal wind at 500 millibars that you're seeing. And I hope you can see my cursor here, but the shading of the anomalies in the wintertime, this is showing you a southward shift in the jet stream. The climatological values for the zonal wind are in the contours here. So this is a de-intensification of the westerlies on the northern flank and an intensification on the southern flank. So that's sort of showing you that southward shift that everybody's been alluding to, and that as a result leads to a pretty marked shift in West Coast precipitation. And so you can see the dipole, that dipole of wetter northwest and I'm sorry, drier northwest and wetter southwest. And that seems to align in our model with the proxy estimates really well, which we show in those circles there. So our model seems to be doing something reasonable. And it's not particularly an outlier, especially among other models forced with similar boundary conditions. We can look at the ensemble mean from the PMIP3 archive. It's the same sort of LGM minus Holocene mean state differences, and you can see a very similar response. So our model is doing something sensible, which is good. But now let's start to peel back the layers and look at individual forcing from the different ice sheet characteristics to see, can we tease out why this is happening relative to these different ice sheet characteristics. So we're going to start with the simplest case. We'll look at the Green Mountain, which is just, as I said, a big bump on North America. It doesn't have that albedo forcing, so it's primarily just mechanical forcing of the ice sheet on the large scale atmospheric climate system. And we'll again start with even the simplest case of that. We're going to look at just the AGCM setup. Okay, so this is a bump on North America, and it's making the atmosphere adjust, but there's no ocean to talk to. There's no communication between the ocean and the atmosphere here. And what you see is something very similar to what we saw in the LGM full case. You see that southward shift in the jet. You see a shift in West Coast precipitation that looks comparable to the LGM full case. And you know what, if this is all the information that we had, it would be job done, right? I mean, this is sort of the signal that has been shown in many other papers looking at sort of atmospheric only simulations. But this is a little bit misleading, I think, because I think it's getting the right answer, but maybe for the wrong reasons. And that becomes apparent as soon as you start to couple this sort of boundary condition simulation to a realistic ocean setup. So these are the same boundary condition force simulations in Green Mountain, but now we're coupling our atmospheric model to either a slab ocean in the middle row or a dynamical ocean on the bottom row. First of all, you'll notice that they aren't that different. So this says that the effects that air-sea coupling are having on the large-scale climate response is mostly happening through air-sea fluxes. Ocean dynamics are sort of a secondary role here. But what you'll see is that really this southward shift in the jet stream goes away. You just see a broad weakening of the westerlies, and you actually see the opposite hydroclimate response along the West Coast. You see a drying, bulk drying of sort of the Western United States and maybe a little moistening of the Pacific Northwest. So this is not the right answer. So let's keep digging and see if we can get a little bit closer. Let's now add some complexity and now add that additional thermodynamic forcing on top of the mechanical forcing using our White Mountain simulation. All right, so we'll look at the White Mountain simulation in the AGCM setup, and you'll notice that it looks very similar to the Green Mountain AGCM setup. So what that means is that the addition of albedo forcing didn't change anything, which means that mechanical forcing is the primary dominant driver of what's going on in White Mountain AGCM. So albedo forcing didn't change the response at all. However, albedo forcing, what it does is it drastically changes the climate response when it's coupled to a realistic ocean setting. When you couple a White Mountain to a realistic ocean, you start to see a much more robust or reinforced southward shift of the jet, and you see a much more coherent north-south shift in hydroclimate along the US West Coast. So it gets two check marks here, right? Not only is it the signal that we were expecting or that we might expect from proxy reconstructions, but it's also in a much more realistic setting where you have a fully dynamical coupled ocean. And when we compare back to our large scale, our LGM full simulation, you can see that the White Mountain dynamical ocean model simulation compares really well. So even in the full gauntlet of boundary conditions that you could change for the LGM, most of the shift that we're seeing in the atmospheric circulation and in the hydroclimate is coming from a tall, bright ice sheet. So the ice sheet forcing basically. So this was a lot, but I just want to summarize for you what we've learned from these two simulations. So we learned that mechanical ice sheet forcing alone cannot explain US West Coast LGM hydroclimate shifts. It can in an uncoupled world, but if you want to think about something realistic, like a fully coupled climate system, mechanical ice sheet forcing alone cannot do that. As soon as you add a coupled system, you weaken the whole westerlies across the North Pacific and you don't get the correct hydroclimate response, at least in this model. Again, huge caveats here. This is a single model simulation. We also learned that the coupled climate system response to direct thermodynamic ice sheet forcing is essential to getting the response that we expect from proxy reconstruction. So not only is thermodynamic ice sheet forcing important, but it's the coupled climate system response to that thermodynamic ice sheet forcing that is the important part here. Okay, so now we're back to the original question, why? Why does the coupled climate system clobber the Green Mountain response? You know, whenever you do couple a Green Mountain to a realistic ocean, why does that ruin the shift in the jet? Also, why does the coupled climate response to thermodynamic ice sheet forcing enable, you know, a reinforcement of the southward shift of the jet that you might have expected from, you know, a mechanically a rock in a stream type response? And so to answer that question, we can start to think about how the ocean and the atmosphere are interacting, and it's primarily through that really thin layer of the ocean that's communicating with the atmosphere, primarily its temperatures. So we're going to think about sea surface temperatures in this case. So let's look at sea surface temperature maps here. These are annual mean sea surface temperature anomalies between our LGM full experiment in CSM1, as well as the ensemble mean of the PMIP3 archive. Hopefully some of you have seen these sorts of maps before, but this is not a new result necessarily. It's been shown in PMIP4, it's been shown in other proxy reconstructions, and the data assimilated work by Jess Tierney et al. Basically, you see this cooling of the Kuroshio of the North Pacific that follows along the Kuroshio extension. And what that does is it increases the meridional temperature gradient between the equator and about 45 degrees north. And when you do that, you accelerate, you tend to accelerate the westerlies, you know, through thermal wind balance, which would reinforce a southward shift of the jet because you're accelerating the westerlies on the southern flank of sort of the climatological position of the jet. So this SST pattern, you know, in a coupled sense, it sort of jives with our expectations of how the coupled climate system would look given that southward shift of the jet. But when we look at our single forcing experiments, we get very different responses between a Green Mountain and a White Mountain. So if you look at the SST response in the Green Mountain, you see that there's mostly this subpolar warming. And I don't have time to get into the details of why you get the subpolar warming, but what ends up happening is you get this, instead of a decrease or an increase in the meridional temperature gradient, you're decreasing the meridional temperature gradient. And through thermal wind, that will decrease the strength of the westerlies throughout the atmospheric column, leading to that, you know, that broad weakening of the westerlies that we saw on the maps earlier. Whereas the White Mountain case, we see an SST map that looks a lot like the LGM full scenario here. So the White Mountain is clearly doing something right. But as I keep saying, this is a coupled system, right? So it's we have to be able to diagnose why this SST pattern is happening. And it's kind of complicated to do that when the atmosphere is driving the ocean, but I'm also claiming that the ocean is driving the atmosphere. So really we need to decompose it through this sort of little flow chart here, right? We have an ice sheet, it has thermodynamic forcing. There is some atmospheric response to that forcing, which is currently, as I'm in the middle of this presentation, unknown. The ocean will adjust to that atmospheric response to the ice sheet. And that gives you an SST pattern. And then I'm claiming that the SST pattern then helps the atmosphere adjust and drive a jet shift. So the atmosphere is then going to adjust to that ocean adjustment, right? Because they want to be in equilibrium in a coupled climate system. So the first part of this presentation, I've mostly focused on these last two little bullet points here, but now we need to think about what is the direct atmospheric response to thermodynamic ice sheet forcing, and how does that create an SST pattern to begin with? And the way that we're going to do that is by looking at seasonal atmospheric circulation anomalies. So what I'm showing you here are JJA, so summertime stationary wave patterns in our White Mountain simulation across the different ocean configurations. And if you haven't seen maps like this before, it's not a big deal. Just think about, you can ignore the contours, just focus on the shading. Think about these as high and low pressure centers. Basically what this is showing is that in each of our ocean configurations in the summertime, a tall, bright ice sheet is creating this cyclonic circulation at lower levels. It gives you this counterclockwise rotation in the atmosphere, which it does make sense for a southward shifted jet because you're decelerating the westerlies up here and you're accelerating them down here. So that's your southward shift in the jet stream. But what's important in this map here is that the circulation anomalies are all the same across all of the atmosphere, across all of the ocean configurations. And that suggests that during the summertime, the large scale atmospheric circulation is largely uncoupled from the ocean, right? The ocean and the atmosphere are not communicating in the summertime. And this jives with what our expectations for modern day climate too. Air-sea coupling is a lot harder in the summer than it is in the winter for a variety of different reasons. But this says that if we can connect back our SST pattern back to, atmospheric circulation changes in the summertime, then even in our coupled simulations, we can get a sense for how direct thermodynamic forcing from the ice sheet is influencing the atmosphere for the first time, imprinting on the ocean, and then coupling back in the winter to give us our our jet shift. And so in the paper, like I said, I don't have a ton of time to go through every detail here, but in the paper, we do this mixed layer heat budget analysis to isolate different physical mechanisms that drive that SST pattern. And I'll just sort of highlight the most important factor that we find for this cooling that we see along the Kuroshio extension, and it's related to changes in shortwave radiation. So let's zoom in on shortwave radiation as a fundamental driver of SST change in our White Mountain simulation. These are annual mean SST anomalies that are implied by changes in shortwave radiation. So this is shortwave radiative forcing. This is top left panel here is showing you the full shortwave radiative forcing. The middle panel here is showing you cloud shortwave radiative forcing. So you can break up the full shortwave into cloud contributions and clear sky contributions. And basically what this is showing you is that there is a response of the atmospheric or the climate system to thermodynamic ice sheet forcing to increase low clouds in this model. So if you increase low clouds, you decrease the amount of sunlight coming at the surface, and that cools SSTs. Again, right, this is a coupled model, and low clouds and SST in the North Pacific are extremely coupled to each other. If you increase low clouds, you decrease SST, which makes the boundary layer more stable, which increases clouds, decreases SST, and so on. So this is a positive feedback. We call it low cloud SST feedback. So once again, we still don't have, we don't have the smoking gun. We don't have a direct atmospheric response to that thermodynamic ice sheet because this is still a coupled climate system. But where we do have that is in our AGCM simulation. Our AGCM simulation doesn't have an ocean. It doesn't have these low cloud SST feedbacks in it. But what it does have is it still has a direct atmospheric response to the thermodynamic ice sheet where it's creating an increase in low clouds. And if you can translate that into an implied SST anomaly due to that change in cloud radiative forcing, and that's what we see. That's what we see here. And you can see that it looks very similar to the DOM, the White Mountain Dynamical Ocean Model experiment. And the only difference between the amplitudes here are the difference between the amplitudes is telling you how important those low cloud SST feedbacks are. In the Dynamical Ocean Model system, both the SST and the cloud responses are amplified because of the feedbacks. But in the AGCM case, all you get is the cloud response. You don't get any of the feedbacks related to the SST. And what's so cool about this is that if you average low cloud fraction in this box in both cases, you can get a sense for what time of the year this is most important. So this is what we're showing down here. This is fractional change in low cloud fraction as a function of month in our model simulations. So these are all relative to the control. So this is like some fraction above modern. So this is like 20% more or less or what. It's all positive, so it's all more. But basically what you see is that in the AGCM case, you're basically only getting an increase in low cloud fraction in the summertime when the ocean is largely uncoupled from the large scale atmospheric circulation. So this is our smoking gun, right? This is saying that in the summertime, large scale response to thermodynamic ice sheet forcing is increasing low clouds at the surface, which through low cloud SST feedback is amplifying the SST signal. So it's allowed to make it to the wintertime where it's able to couple back and influence the large scale, the jet and ultimately the hydroclimate on the West Coast. So again, the difference between these two things is an indication of how strong those low cloud SST feedbacks are in making the signal much stronger in the dynamical ocean model than it is in the AGCM case. All right, so summary here. This is just sort of our interpretation of the complete coupled climate system response to a tall, bright ice sheet. So in the summertime, when you have the most insulation to reflect to begin with, you get a strong diabatic heating response to this ice sheet. Part of the fundamental response to a tall, bright ice sheet in the North Pacific is this low-level cyclonic circulation that advects cold air from the high latitudes over the western North Pacific. It also advects moisture from the tropics on the eastern North Pacific. And both of those things are good at creating increased low clouds because you increase stability at low levels from the cold air advection, but you're also increasing moisture content in the eastern North Pacific. So you end up increasing low clouds, decreasing SST at the surface. Low cloud SST feedback takes over, it ramps up both of those signals, allowing those SSTs to build up, to persist, make it to the winter time where the atmosphere then adjusts to that atmospheric forcing, to that ocean forcing. The ocean couples back to the atmosphere, and through through increasing that meridional gradient between the equator and about 45 degrees north, you accelerate the westerlies on the southern flank of the jet, and it helps to reinforce an otherwise mechanical forcing of the jet. That mechanical forcing of the jet is still there. It's still underneath there in an uncoupled sense, but you need that coupled response to thermodynamic forcing to reinforce it and ultimately to meet our expectations that are built up from the proxy reconstructions. So I am way over time, so I'm sorry about that, but I'm happy to take any questions or just leave it for discussion. Thanks.
Well, we could probably do one question quick. I have to say I'm really disappointed in this because teaching about the split jet and hosing water into the Southwest to raise the pluvial lakes, that was a real easy teaching thing. You could even get undergrads to kind of picture that in their mind. Now here it is. It's going to take a little bit more time to explain. So do we have one question?
It looks like Tony has a question.
Yeah, Dylan, I do. Thanks for a nice talk. My question is about the AGCM experiment with the Green Mountain.
Mm-hmm.
What are the sea surface temperatures in that experiment?
What are they?
Yeah, I mean, it's an atmosphere only, right? So you have to prescribe sea surface temperatures.
They're fixed to the pre-industrial control climatology.
Okay.
And I think that's also true of the White Mountain case. So in all of our AGCM simulations, they're all fixed to the pre-industrial control.
Okay, thank you.
Mm-hmm.